class, hope you're doing well. So today let's talk about ANCOVA. Strange name, but pretty cool stuff. And so today what we're going to do is to go over the conceptual information about what ANCOVA is and what it does. And then we'll do a quick demo using the wellness dataset again. And I would encourage you to keep the code open in RStudio and follow along. Since we're just going to conclude with a summary this time, we're not going to do a walkthrough with a your turn exercise so that we can keep room open for other tasks that you have to do for the remainder of the week. And so please follow along and make sure that you become familiar with this type of analysis. So let's get started. Now, ANCOVA is short for Analysis of Covariance, and it's really ANOVA after controlling for the effects of covariates. Now, what are covariates? They are variables whose effects you want to control for or take out before testing the effects of a factor. So let me explain a little bit more what I mean. So covariates are variables that might influence the dependent variable, but they're not your variables of interest, and so you don't want to test hypotheses about them, but you want to take their effects out because they influence your dependent variable. And so here's an example. Now let's say that you wanted to examine the effect of eating breakfast or not eating breakfast on processing speed. Now in clinical psychology assessments, processing speed is often measured as how quickly you can complete visual motor tasks. And so you can imagine that if the person didn't get good night's rest before, that person might be a little bit more compromised or slow down. And so maybe you want to control for hours of sleep that the participant got the night before. Now, you're not testing any hypotheses about sleep itself. It's not an independent variable, but it's a covariate. And so you know that sleep might affect processing speed, so you want to account for that effect first and take that out. And see if sleep is held constant, all things being equal about sleep, whether or not eating breakfast affects processing speed. Now, why might you include covariates when using ANOVA? There are a couple of common reasons. One of them is mathematical, so it increases your ability to detect differences. And so you might remember that the F statistic is the ratio between mean square between and mean square within. Now, typically, mean square within is everything else under the sun that's not accounted for by the systematic group difference, which is MS between. And so typically it would look like this, where the ratio would be between group variance here and then the within group variance here. Now, if you account for the covariate and then take that out of what's in the denominator, then you would get this. So now if you were to calculate this ratio of MS between and MS error, then you would be taking a ratio between what's under group here, so the green stuff, over what's in this section, error. And so the denominator of your F statistic gets smaller. Now, what would that do for the F statistic if the denominator gets smaller? If the denominator is smaller, then the F statistic would get bigger, wouldn't it? And so the greater your F statistic, the more likely that you would be able to reject your null hypothesis, all things being equal. And so that makes your test a bit more powerful to detect differences. And another reason why you might include covariates ANOVA is to eliminate confounding variables. And so confounding variables might affect the relationship between your IV and DV and kind of alter it. And maybe you want a more undiluted, direct relationship to test between IV and DV, and so you want to take out the effects of the confounding variables and account for them already. And then you can get a cleaner test, if you will, of the relationship between your IV and DV. And so these were a couple of the reasons why researchers might want to include covariates, and so use an ANCOVA design instead of an ANOVA design. Let's talk about what happens under the hood a little bit. And so what RStudio is doing for you under the hood is that it's combining regression and ANOVA. First, what it's doing is to regress the dependent variable on covariates. That's another way to say that it's running a regression where the covariates are the independent variable and the dependent variable is the outcome. And so it regresses DV on the covariates as if the covariates are independent variables. And then it uses the leftover variance or residuals to test for the effects of IVs in ANOVA. And so that's what RStudio is doing under the hood when you run an ANCOVA. Now let's take a look at some key assumptions that are required and assumed when you run an ANCOVA. First of all, there's a linear relationship between covariates and DV. And so, for example, covariates do not have a curvilinear or quadratic relationship. It is a linear relationship. And this you can check using the plot function with a scatter plot if you like. That there's homogeneity of variance, and you already know how to test for that using Levene's test. That they're normally distributed residuals, and so you can do this in a manner very similar to what you did for simple regression. And here's a new one, homogeneity of slopes. So the regression lines describing the relationship between covariate and DV are parallel for all levels of the IV. And so essentially the linear relationship between covariates and DV do not change based on the different levels of the IV. Now, this is a new one that you can check for if you like by looking at the interaction term between the IV and the covariates, and I've given you a form with which to do so in RStudio. And so this is one thing that you can check also for the assumptions of ANCOVA. Okay, so now that you have the background information for ANCOVA, let's go ahead and take a look at a demo together. And for this, I would encourage you to make sure that you have the dataset and the lecture code open so that you can follow along and pretend as if you're running these analyses on your own. And so going back to the wellness dataset, let's say that you had the research question, does self-reported well-being, so the variable well-being, differ by coping strategies used? And so that is defined by the variable condition, which had 3 levels. One represented acceptance and commitment therapy-based strategy, another represented cognitive behavioral therapy-based strategy, and then there was a control condition, so 3 levels, after controlling for the effects of baseline stress, so taking away the effects of the baseline levels of stress that each individual brought into the study, what was the effect of condition on well-being? And so the variables are broken down like this. And so considering these variables, let's talk about hypotheses. And so first of all, the null hypothesis. The null hypothesis would say that those 3 conditions for your independent variable did not differ in well-being ratings on average. And then the alternate hypothesis would say that there actually was some sort of a difference in average well-being ratings across those 3 conditions. And so there was at least one mean difference that was found in well-being, would be the alternate hypothesis. And these would be true after controlling for the baseline stress level. So we are controlling for a continuous covariate on top of an ANOVA situation, which you're now very familiar with. So let's talk about running ANCOVA in RStudio. And so some of this will look vaguely familiar, but we're going to make some adjustments. And so you would first save your model into an object. And so you would use the lm function again. But this time, instead of just regressing y on x, you would regress y on covariate, and then with plus independent variable x. And so lm, and then this is your dependent variable, and then regressed on covariate, and then with a plus sign, also mention the IV. And then you would get the ANOVA table using the ANOVA function. But this time, ANOVA is capitalized because it's a function that is inside the package car. And so you'd first want to load the package car by using this library function. Now, if you haven't installed the package car, then you'd want to do that first. But then, assuming that you already have it installed, you'd want to use the library function to load the package car, which will give you access to the ANOVA function. And then you would mention the object in which your ANCOVA model is saved, and comma, and then type equals, and then this is capital II, or type 2 error. This type 2 error is saying that you would like to test for main effects of your independent variable and covariate without assuming that they are completely independent of one another. So this is the way to get a good sense of what happens when you have the covariate and the independent variable both predicting your dependent variable. And so that's the reason why we're using type equals and then in quotation marks II, so capital II, type 2 error. And so let's hop on over to RStudio and take a look and see what it looks like. See you there. Alright, so here we are back in our trusty old RStudio, and I have set up my environment by reading in the dataset wellness again, and then I've attached the dataset so that I don't have to keep on doing the wellness $, and then the variable name type convention. And so let's now start writing our ANCOVA model. And so you might remember that we used the ln function again, but we want to save that model. Now, what should we call it? Something creative. Just kidding. I usually just name models in really just kind of straightforward ways. And as long as you don't use a name that conflicts with whatever is in the vocabulary of R that conflicts with something, it's perfectly fine to just name it however you wish. And so you might remember the ln function. And so our dependent variable is well-being. And then we regress that on the covariate first. And so covariate is stress. And to that, we add our independent variable, which is condition. And so let's try running that. And it ran, no complaints. We're off to a good start. And then in order to get the ANCOVA output, though, you will remember that you want to load the package car. And so I loaded the package car. I have it already pre-installed. And then you just want to do the ANOVA function this time. You will want to first name the model, comma, and then include type equals 2. And that will allow you to get the ANCOVA result. Fingers crossed. Let's see. Ran it. All right. And so here we are. And so this is our table that shows the ANCOVA results. And so let's talk about this by breaking it down in PowerPoint. And so meet you over at PowerPoint. So here is our ANCOVA output. And the main place you want to pay attention to is the line that includes your independent variable. And so here for condition, you can see its F statistic and then the p-value associated with it. So you can evaluate your hypothesis about the impact of your independent variable. And you will also want to pay attention to the degrees of freedom that's associated with the area called residuals. That is the error or the within group variance term. And so we will want that information when we write up the results in APA style coming up in a couple slides. But first of all, let's evaluate our hypothesis. And so if you have this F statistic with this p-value, 0.07, then we notice that p is greater than our alpha of 0.05. And so what do you conclude? Do you reject or retain the null hypothesis? You retain the null hypothesis, right? And so, bummer, we cannot reject the null hypothesis. And so the independent variable of condition does not have a significant effect. Translating that to APA style, right up here is a sample for you. Once again, we use the same format as what we used for one-way ANOVA. And so the numbers came in where the degrees of freedom tables over here, the numerator degrees of freedom of 2 came from your IV, and then 195, which is the denominator degrees of freedom, came from the residuals line. And the F statistic and the p-value associated with that can be found on the line where your independent variable is, which is condition in our instance. And so after controlling for the effect of baseline stress, condition did not have a significant effect on well-being. And then here's the write-up. Now, if you would humor me, let's just go into an alternate universe where condition happened to be significant. So your independent variable was significant. And so let's make believe with me. And let's talk about how to run a post-hoc test. And so again, this is an imaginary scenario, but let's imagine that the condition variable was significant, in which case you want to run a post-hoc test to figure out where the mean differences were. And so let's talk a little bit about that. How do you run it in RStudio, first of all? Now, for ANCOVA, we're going to use the function glht in order to run the post-hoc test. That will give you the two-keys method of doing a post-hoc test. In order to run the glht function, though, you first need to install and load the multcomp package, multcomp, multcomp. And so you'd want to first do that and then make sure to load it so that RStudio will recognize the function glht. Once you have the multcomp package open, then you'll be able to run the glht function. And just like you save models to objects, when you run, say, ANCOVA or ANOVA, you'd want to do that here as well. So you'd want to save this whole model into an object. And so here, glht, and then inside the function parentheses, you'd want to tell RStudio which ANCOVA model you are referring to. And then you can fill in the rest. And here is where the independent variable name would go. And then once you save that model, then you can get a summary for that to get the post-hoc results. And so this model that is saved into that object goes in here. Now, something that's a little tricky about glht, though, is that it requires the independent variable to be recognized as the factor variable. And so right now we have condition, but condition is a text variable with 3 values. In order to run the glht function, you want to tell RStudio that your independent variable is a factor. And so you can do that using the asFactor function. And so let's go ahead and begin to follow these steps. I'll see you over at RStudio. The funnest studio there is, right? Okay, so here we are back in RStudio, and we are making believe that you had a significant independent variable, which is condition. So let's try running a post-hoc test and see what that looks like. And so you know that we need to install the montcomp package and then load it. And so I think I might have this already installed, but I'm just going to run it again. You can always go to packages and then install to install any new packages. And then you will want to load it once you get it. Interesting. So here we are. Now let's try running the glht function, and I will show you what happens if we don't do asFactor. And my assumption is that it's going to lead to some errors. I'm just going to do it in the console so that I can just kind of see, what happens, and then we'll work on the code itself. But so you will remember that you will want to save your model. And so let's say I am saving a post-hoc model. Remember that you can type your functions into console and run your code without saving it as part of your script. So I often will doodle here to just kind of see what happens. And I think that should be fine. And then we're going to use the function glht. And then the ANCOVA model name was ANCOVA model. Then there's this lymphct function. And what we want to do is MCP, and you can always go back to either my lecture code or the lecture slides to figure out what was typed in. But right now we have the variable condition. And then you want to run tukey. And so I think that should be the completion of that line. And let's try running it. And you can see that it will complain that condition is not contained as a factor in this model. And so it's asking, what are you doing? You are, running this analysis, but your variable condition is not recognized as a categorical factor variable in R. And so we want to backtrack and designate this condition variable as factor. And technically, we're actually going to save another version of it that is recognized as factor. So almost like making a copy. And so if you have already attached the data set, you might want to detach it first of all. And so I'm going to detach it. And so first of all, we want to tell R what the destination variable is going to be. And so let's say wellness, and then you don't have to do something like this. You could do, confac or whatever it is that is easiest. For just kind of ease of memory, I'm just going to keep it, as written out. But usually I would shorthand a lot of variable names. asFactor. And then remember that we are not attaching this data set anymore. So we want to tell R what variable we're talking about by designating the dataset name and then $, and then condition as a variable. And let's see if we run this, does it save a variable called condition factor within that dataset for us? Here we go. And so you can see the difference here. It's recognizing that there are 3 levels in this categorical variable factor, designated as factor in RStudio or R. And so we're going to attach that wellness dataset again. And then we're ready to work with condition factor as being part of that data set. All right. And so what you want to do, and so you can see my notes over here, you want to rerun that ANCOVA with the updated factor. And so we will do that. And so let's say ANCOVA model 1, creative. And so the dependent variable, once again, is well-being. And then the covariate, as you might remember, is stress. And then this independent variable now will be that factor variable. And so in this case, it will be condition factor. Keep in mind that I knew that this was written all in lowercase, but R is case sensitive, and so make sure that you are using the correct case for whatever factor variable you have saved. And so we are now saving another ANCOVA model, but this time the independent variable is the factor variable. And so basically a copy of the condition variable that's been designated as a factor variable, a categorical variable with 3 levels. And so just the way R is classifying that variable is a little different than the original variable of condition, which was just a text variable. Let's rerun that. And so it ran. And then we are ready to run that post-hoc test. And so let's say, post-hoc model 1, and then the model is just updating the code notes that I have, and then the linking function, I suppose, is probably what it's talking about. And then condition factor, and so remember to put in the factor variable, and then Tukey, and then you want to get a summary of that. And so let's try running that and see what happens. Ta-da! And so here we are with the post-hoc test. And so this is a make-believe scenario, and so you're not going to see any significant p-values for any of them. But this one is kind of almost marginally close to being significant, 0.06, and so you see a dot there because p is less than 0.1. But what it tells you is where there were significant differences. And so you want to look at the p-value and compare, which ones had a p-value that is less than your alpha. We were, in this make-believe land, let's imagine that this was significant and p-value happened to be less than 0.05, in which case you will know that these two conditions were the ones that were different. And then there were no differences in these comparisons. And so it's basically doing pairwise comparisons across your different levels of your factor. And then it's going to point out which comparisons had a significant mean difference. And so hope that makes sense. And so look for the significant p-values. So p-values less than your alpha, or usually 0.05. And then look at the comparison, which two groups are being compared. And you will know that those two groups differed significantly. Now, when you're doing your write-up and just thinking about all of this, you will probably want to see the actual means for those groups. So I wanted to kind of show you one way to get means by group. And so I've written out code for these. And so you can use the aggregate function to have our list means by group. And so this is pretty handy, and so you will want to keep this in your notebook sometime. And so what goes in here is the dependent variable, first of all, comma. And then there is a by. And so, show me the dependent variable by, grouped by, and then list. And so in this instance, you can use whichever, whichever variable. And so it will lead to the same results, basically. So I will show you kind of two different versions here, but it will be the same thing. And then comma, and then let us know, sort of let R know which type of statistic you should be seeing by group. And so let's run these guys. So let's try running the mean first, because that's usually the most important part. And so here we are. And so now this shows you the mean of your dependent variable, well-being, by each level of your factor or group. And so this is the ACT group, this is the CBT group, and then the control group under the variable condition. And so you can see that, if you kind of eyeball it even, you can see that the difference between CBT and ACT are the greatest when you do pairwise comparisons. Oftentimes when you report means in APA style, you will also probably want standard deviations. No problem. Just ask for standard deviation by group. And so you can run that for SD at the end of your aggregate function, and then here are the standard deviations for each group. And so that will make it easier to write these out in descriptive statistics style when you report your results in APA style. So there you have it. So let's go back to RStudio. I can't believe I just said that. Let's go back to PowerPoint once more and begin to put it all together and wrap up. See you there. So a quick review on how to interpret the glht summary output. You want to look at the p-values for pairwise comparisons, and if p is less than 0.05 for your alpha, then there's a significant difference, and you can look across and see which pairwise comparisons had a significant difference based on the p-value that's associated with it. Now this is all just kind of imaginary data, but let's say that you wanted to report your post-hoc test results in writing. And so in this case, you had a significant result in theory. And so I've just made up some statistics here. Similar format as before, but then you would add the results of your post-hoc test. And so you can just say post-hoc comparisons using the Tukey method, reveal that, and then just explain which groups significantly differed from one another. And it's usually pretty helpful to have the mean and standard deviations reported for each group so that the reader can eyeball the magnitude of the difference and just kind of interpret it for themselves. And as you know, you can use the aggregate function to obtain these group means and standard deviations. And so great job today learning about ANCOVA. And a quick summary. What is one-way ANCOVA? It is basically one-way ANOVA when you want to control for continuous covariates. You would have one continuous DV and one categorical IV as before, so that's the one-way ANOVA setup. But in this instance, you can control for one or more continuous covariates and take out their effects from your dependent variable before testing for the effect of your categorical IV. And so that is pretty cool. And the interpretation is very similar to ANOVA. And if you have a significant independent variable, then you want to run the post-hoc Tukey's test to figure out where the mean differences were. So that's all for now. And so hope you have a great rest of the week and take care. Please let me know if you have any questions. I'll talk to you soon. Bye for now.